So now that we've been working with integration and we've been working with antiderivatives, we've already looked at how to find the antiderivative if we're integrating an indefinite integral. So it does not have an upper and lower limit. We talk about how we add c because it can be a different vertical shifts of a function. Now we're going to look at what do we do if we have a definite integral and we have those limits. Well, that's what we're going to do for that is we're going to use the fundamental theorem of calculus. So all the fundamental theorem of calculus tells us is that we can integrate our integral and find our antiderivative in the exact same way as we did when we had indefinite integrals, and then we'll plug in our upper limit, subtract, and plug in our lower limit. That is what that is saying here. Oftentimes when we write it, the notation we write, instead of writing f of b minus f of a, because if you think about what f could be, it has the potential to be a very long function, and it gets repetitive to keep rewriting that. A lot of times the notation we'll use is this here. So I only have 2 examples on this because it is fairly similar to what we've done already. We will do some work on it in class the following day, so if you have questions, please make sure you bring them, or you would like me to go through some more examples with you, please let me know that so I can do that. Let's look at this first example though. So as I said momentarily ago, first thing I'm going to do is integrate this as if there were not those upper and lower limits. So in order to integrate this, I'm going to have to go ahead and distribute that x in, because remember, I do not have any kind of a fancy product rule. So I'm going to just rewrite my function without doing any integrating. And now I can go ahead and use my power rule that says I'm going to take my current exponent of 2 and of 1. I'm going to add 1 to that. I'm also going to divide by that quantity. I'm going to add 1 to 1. I'm going to divide by that quantity. So I'm going to have the integral, I'm integrating, so I no longer need my integration sign. So I'm going to have 2 over 3x cubed minus, I'm going to end up with, I'll go ahead and write it out instead so you can see. So 4 over 2, and then I'll simplify, x squared. And using that notation I was just talking about, I'm going to take that function and I'm going to go from 1 to 4. And notice I do not need the plus c. So first thing I'm going to do is I'm going to plug 4 into my function. So plugging 4 in, I'm going to have 2/3 times 4 cubed, which is times 64. And I see 4 over 2 is going to reduce to 2, so minus 2 and times 16. And according to my formula, after I plug the top limit in, I'm then going to subtract and plug the bottom one in. So I'm going to say minus, and I plug 1 in. So 2/3 times 1 cubed is 2/3, minus 2 times 1 squared is minus 2. And going ahead and doing my math, I have 2 times 64 is 128 over 3. And 2 times 16 is 32, times 3 is going to be 96 over 3, going ahead and getting that common denominator. Minus 2 over 3 minus, again, getting my common denominator. That's going to go ahead and give me 32 over 3 minus a negative 4 over 3. Which ends up being 36 over 3, which is just 12. And I'm going to go ahead and do the same thing on example 2. So first thing I'm going to do is I'm going to go ahead and integrate. Notice in the first one I had to rewrite my function in order to integrate. On this one I don't have to. So I say, what does secant squared integrate to? And maybe I start racking my brain and I start thinking about ways I can rewrite this, and then I realize that we have those lists of trig functions that I believe it was a gray box in your books, and off the top of my head I cannot remember what page that was on, but you guys marked it in your text. I look that up and I see that secant squared, or maybe I've just used it enough now that I've actually even got it down on my own. I don't even have to look it up in the book, but I know that that integrates to be tangent of x. So this integrates to become tangent of x, and I'm going to go from 0 to 5 pi over 4. So I always plug my top one in first. So then I'm going to have tangent of 5 pi over 4 minus tangent of 0. So tangent of 5 pi over 4, I go to my unit circle and I see at 5 pi over 4, sine and cosine are the same. So when I put those together, same number minus same number, it ends up being, I believe, negative square root of 2 over 2 minus negative square root of 2 over 2 ends up being 0. Minus at tangent of 0. I have sine over cosine. Sine is 0, so I have 0 over 1 is 0, and this is not correct. I'm sorry, I don't subtract. Tangent of 5 over 4 is sine over cosine, and since they're the same, negative square root of 2 over 2 divided by negative square root of 2 over 2, I end up with 1. Sorry about that. And I get 1 minus 0 for a final answer of 1. So again, notice it's exactly the same. All of my same rules apply, so I can kind of fix or rewrite my function first like I did in the first example. I can do distributing. I can do each piece separately if it's adding or subtracting. I can use all those trig formulas that I used before. Absolutely nothing changes except for the fact that I don't add the c, and I can't stop after my integrating is done. I have to continue by plugging in my upper limit and my lower limit and subtracting the two values from one another.